So, I will start with what I hope will be the most boring part of this presentation. I will introduce myself. So, my name is Vladik Khononov. I came here from Israel. I worked in our industry for almost 20 years, 9 of them in the role of software architect. And software architecture is not only my job, but it also became a hobby. I really love, researching this topic, blogging about it, and of course, speaking at conferences like this. Today, I want to talk about messaging, and more specifically about the architectural pattern we usually call events. And the thing is, events, they're like everywhere nowadays. Event-driven architecture is based on events. Event sourcing, finally getting the attention it deserves, it's also based on events. Microservices are everywhere, and many are calling for integrating them asynchronously through events as well. However, this popularity came with a cost. Somehow, many see the events as some kind of, secret sauce for preparing distributed systems. As if you can take a monolith, pour some events over it, and boom, you've got yourself microservices, domain-driven design, and of course, modern architecture. Of course, it's not really true. Events are not some magic, but they're just a tool. And as any tool, it can be used to create some great stuff, but if you are going to abuse it or misuse it, it's a great way to take your legs off. And actually, I have experience of doing both. So in the next hour, I want to share with you my experience, the mistakes I did, how we were able to fix them, and most importantly, what we've learned from this experience. And I hope it will be helpful to you and you will be able to skip this learning phase. And since we are talking about an architectural pattern, I want to start from the basics to make sure that we are on the same page about what is software architecture, what are its goals, and how to evaluate software architecture. Like, what's the difference between a good one and a bad one? Then we'll do the same for the event pattern. Again, we'll see the definition of this pattern, what an event is. And we also see that not all events are made the same, and instead, actually, there are 3 types or flavors of events which are used for messaging. Next, I will share some scary war stories on how distributed system design can go wrong. And of course, this discussion will be based heavily on the preceding theoretical part on software architecture and events. And I will finish with 3 heuristics, like simple rules of thumb that I'm using today when applying messaging, to evaluate and keep distributed system architecture on track. So, without further ado, what is software architecture? And when answering this question, usually 2 quotes come to mind. The first one is by Ralph Johnson, who said that architecture is about the important stuff, whatever that is. And Martin Fowler, who said that software architecture is those decisions which are both important and hard to change. Now, both these authors stress the importance of architecture. And I guess no one would argue with that, right? We build software not for expressing ourselves, but to solve business problems for organizations which are going to be using this software. And software can make companies more efficient. It can increase their competitive advantage, profitability, and in some cases, software even enables the business itself. For example, when software is the product that company is selling. Therefore, robust software architecture and design is not something which is nice to have. Instead, it's crucial for the success not only of the system, but of the whole organization that is going to be serving. And that's what makes those architectural decisions so important and unfortunately hard. For example, 8 years ago, I was the first employee of a company called Internovus. And I had to plan and design its architecture from scratch. So we had to decide whether to use self-managed servers or go to the cloud. Those are like the old days before cloud was cool. We also had to choose whether to dive into the brave new world of NoSQL or to stay where we are most comfortable with relational databases. Of course, we also had to choose languages, frameworks, patterns, architectural styles, etc. Now, not only these decisions were hard, but they also involved lots of risk. One wrong step could make the system way more complex to implement and to maintain, both in short and long terms. Therefore, in my opinion, the goal of software architecture is to manage systems complexity. And we manage this architectural complexity by decomposing systems into sets of interconnected components, modules. Those modules can appear at different levels. They can be methods, classes, namespaces, services, and even whole systems. But in this presentation, I'll speak about modules in context of microservices. So at whatever levels modules are, they make it easier to reason about responsibility of each module and its interactions with the rest of the system. Moreover, modularity simplifies understanding of the system as a whole. With proper modules, it's easier to grasp what the system is supposed to do and how does it work. On the architectural level, modularity reduces risk of the system's design. It limits the scope of those implementation decisions to the scope of each module. So for one module, you can choose, for example, a relational database. For another one, something more modern. In other words, modularity helps us to manage systems complexity. It does that by dividing this complexity into two parts. The first one is local complexity. Local complexity is complexity of a specific component. And I think the easiest way to demonstrate this idea is, if you have a module and you want to evaluate its local complexity, ask, how hard will it be for a junior team member to grasp what's going on inside of this module? What are its goals? What's the business domain of it? What it's doing and how does it work? For example, in our company, we had a module which was in charge of commissions, calculating commissions for sales agents. And, its public API resembled a coherent set of methods which all of them were related in this way or another to those commissions. On the other hand, we had a much bigger module, and at some point it included logic for managing advertising campaigns, contracts with publishers, creative catalog, and even finances. So, I don't need even a junior team member. Sometimes I would look at it and have no idea what's going on there. Therefore, its local complexity is way, way higher. The second type of systems complexity is global complexity. It is defined by the level of interconnectedness between the system's components. With low interconnectedness, it's easier to understand what role each component plays in the system. And it's also easier to evolve components, since modifications will have lower impact on the rest of the system when you're modifying only one component. Here's an example with relatively, I think it has a low global complexity. It has 5 components, and we can trace all the dependency between them. And on the other hand, here, we have the same number of components, but way more connections between them. And that makes global complexity of this system higher than the previous one. Thus, this process of defining components' boundaries is actually a key architectural decision. Proper boundaries reduce complexity of the system and make it more adaptable to future requirements and changes. So if you go back to the question of what is software architecture, I think Ruth Malan gave a crystal clear answer. She said that system design is inherently about boundaries. What's in, what's out, what spans, and what moves between those boundaries. It reshapes what's outside just as it shapes what is inside. So system design is about drawing components' boundaries. And speaking of what moves between those boundaries, let's talk about events. As I said in the introduction, it's a common practice today to use events for loosening coupling between the system's components, right? And the idea behind this pattern is actually very simple. An event is just a message which is used as a contract for integrating systems. Some system can publish its events, and other systems who are interested in that information can subscribe to those events. Therefore, in this scenario, the event plays the role of integration contract between those systems. Of course, events can take different forms. They can be JSON documents, XML files, protobuf, but whatever way you choose to represent the events, the idea behind them is the same. An event is just a data structure with no behavior attached to it. It only represents something interesting that happened in the past. For example, in our company, we have an event called click, impression, campaign started, a paycheck generated, etc. Now, if you look into what's going on inside of the event, usually it contains its type, some metadata, for example, a timestamp, a name of the system that created it, and of course the payload, the specific content of the event message. However, payload is where those events really differ, and actually there are three types of different events. In his article called What You Mean by Event-Driven, Martin Fowler identifies three types of events. The first one is what he calls event notification. Such event is used to notify that something important has happened. And the key here is to notify. The source system doesn't expect any direct or indirect, maybe indirect, but it doesn't expect any direct response to the event. And in fact, it isn't even aware who the subscribers are for that specific event. Also, such event contains minimal information on nature of the change. For example, what was changed in the system's data because of this event. A subscriber, if it's interested in knowing that information, can execute a query against the source system and to get the more detailed information. In some sense, event notification is like a pager. Everybody knows what a pager is? Good. So here as well, you get an event notification. Okay, some stuff is going on, but you have to call the number to get more detailed information about what's happened. The next type is what Martin Fowler calls event-carried state transfer. And here the originating system notifies that something has happened, but the message contains all the information that was changed because of some business transaction. It can come in two forms. The first one, let's say you have some customer entity, so the event can contain a snapshot of this customer state, the updated state. The second form is to specify what were the fields that actually changed because of the business transaction. So if, for example, you have like 200 different fields and only 2 of them changed, so you just publish what changed and not all of them. In any way, this information is supposed to be sufficient for the subscribers, and they don't have to query the publisher for additional details, as in the case for the event notification. And of course, the obvious advantage of this approach is the considerably lower dependency of subscribers on the publishers. It both makes the subscribers more resilient. They can continue functioning even if the publisher is down for some reason. They have a local snapshot of all the data. And it also lowers the risk on the publishers themselves. So if some subscriber is going crazy and he really needs to process some information many, many times, it's not going to affect the publisher because that subscriber has all data locally. And the final type is the events used for event sourcing. And usually they're called domain events. Do I have to give a small introduction about event sourcing? Yes. Okay, so I'll do it briefly. Event sourcing is a different way of representing system state. If, for example, in traditional systems, we have some database record which represents the current state of some entity of the system. For example, customer ID, I don't know, something, his name is John, last name Johnson, and status. And when you're looking at this record, you know its current state. Event sourcing is a different and kind of interesting way to represent the same data. It includes the dimension of time. So instead of storing the current state, you're storing the complete list of events that led to the state. So the customer was initialized. Then he updated his contact details, etc., etc. And you can always go through those events to calculate the current state. So that's event sourcing 101. So for event sourcing, we are using events as well. Those are usually called domain events. And as I said, each change to a system state is represented by an event. And such events are somewhere in between those previous two types. As notification events, they do notify that something important has happened, but they also have to contain data that describes what actually has happened. This data, however, should be modeled as close as possible to the business domain and not some particular state representation, as in the case of events for carrying changes in state, the previous type. That's why usually when speaking about domain events, people describe them as stateless. Stateless in a sense, as Marianne Duncan-Jones says here, events should be stateless as regards the entity to which event occurred. In other words, money deposited event holds no data on the account balance. If you need the balance, you can always run through those domain events and calculate it from scratch. So those are the three types of events. I will quickly summarize them with a small example. Notification event, again, only signals that something has happened. For example, marriage or divorce. Event carried state transfer is basically a data replication mechanism through events. An example would be personal details changed event. Such event may be fired when a person's last name changes. However, unlike notification event, it would have no connection to the reason, whether it's because a marriage or divorce. It's just the fact his last name was changed. And finally, domain events are somewhere in between. They do reflect the reason, for example, married, and all the related data. But they shouldn't be coupled to a specific state representation. They should reflect as much as possible the business domain and not some kind of a projection of it or model of it. And it's crucial to choose the correct event type for a specific task. Otherwise, instead of modern architecture, you will end up with accidental complexity and even the dreaded distributed monolith. To demonstrate it, I want to share some war and horror stories from the company I've been working at for the last 8 years. As I said, the company is Internovus. And our goal was to allow companies that are producing, for example, products or services to outsource their marketing-related chores. So they will come to us and we'll create advertising materials, we'll publish advertising campaigns, we'll optimize them to make sure that spend the least and they're the most effective, collect the leads from those campaigns, and eventually our sales agents would make the calls to sell our clients' products. Pretty complex and wide business domain. And as it usually happens, initially we try to implement it as one huge monolith. And complexity-wise, the system had very low global complexity because, hey, we have only one component. But this component's local complexity was huge. Everything was in it. And unsurprisingly, after some time, this design started breaking under its own weight. It became slow, hard to test, and overall unpredictable. So at some point, we decided, okay, we cannot take it anymore. We have to break this monolith into two subsystems, marketing and CRM. That's what it looked like. Marketing system, it was in charge of collecting and publishing marketing events. For example, impression, click, submitted lead, etc. And this marketing system was kind of stupid. It didn't really do anything with those events apart from publishing them to the subscribers. The subscribers were free to pick up those events and do whatever they need with that data. So those subscribers included, first of all, our CRM system, our BI department, that wanted to analyze what's going on in our marketing domain, and our clients, organizations that were using our services. They also need to get some notification about marketing events. So those subscribers were free to make their own decisions on how to project those marketing events into some kind of their own state, which is going to be convenient for their needs. Architecturally wise, the goal of this redesign was to lower local complexity of the system's components. And we did. Once we started decoupling those different concerns, local complexity went down. No arguing about that. Now, let's see what happened to the global complexity here. As time passed, we've noticed that this state calculation logic here on the right side, how does it work? Oh, it works. The first time I'm ever using this. So this state calculations, which is performed by all of the subscribers, was duplicated across all of them. Despite the freedom to choose whatever model they need, all of them projected the same data. As a result, the business logic that generated that state was duplicated across all of them, and that introduced what I call logical coupling between these components. This business logic was duplicated across 3 different systems, and it had to change simultaneously. Also, at some point, we were hit in the face by unreliability of network here on the left side, on the publishing side. We naively assume that whatever we are going to publish from the marketing system, all those events will be delivered in the same order as they are published, and they will be delivered exactly once. As if this whole system acts as one big logical transaction. Of course, that's not possible. And the moment things didn't go as planned, the same sets of events produced different results for different subscribers. They had the same business logic that processed them, but because of the nature of network, that some of the events arrived out of order, they calculated different results. Now, to fix this, we had to employ some infrastructural voodoo, you know, which entangle those components even more. And bottom line, whatever you look at it, with this voodoo or without this voodoo, this system has a very high global complexity. All its components are entangled and really strongly coupled to each other. The solution was to refactor marketing into an event source system, and instead of publishing notification events, it emitted some minimal workable state that would be enough for the subscriber's needs. From the events perspective, we went from, I would say, we went from event notification to event carrier state transfer. So instead of throwing raw data on the clients, this service took care of this business logic that projected this state and published these changes in the state to all the consumers through event carrier state transfer. This refactoring lowered both the global complexity of the whole system and the local complexity of its components, because first of all, those subscribers didn't need this state calculation logic anymore. It resided only in one place. So that's what our final decomposition looked like. Marketing emitted event carrier state change events, which were received by those subscribers, and they created their local copies of them and then did their job. Now, speaking of this CRM system in the middle, originally we implemented it in a traditional way. It stores the data in a relational database. However, after some time, this implementation was limiting us in multiple ways. First, it was hard to scale a relational database. Second, it limited us to the relational model, but BI people, they needed a way to get more insight into the data. So they continually bombarded us with some weird requests, add this field here, that field there, calculate the amount of times, for example, a customer changed his phone number and stuff like that. And of course, we had limited success implementing it with this rigid relational model. And third, we wanted to break out of this relational database prison and instead to embrace the polyglot persistent model, to use multiple databases, you know, to get the benefits of each type of databases. Database for cache, for operations, for reading, etc., etc. So to achieve these goals, we refactored this CRM system into an event sourcing and CQRS-based system. Do I need to give you a quick introduction to CQRS, anyone? Okay. So CQRS is a pattern, you know, that allows you to represent the same data in multiple persistent models. And that's what our initial implementation looked like. It was pretty much by the book. So the client would submit a command. Its execution would result in new domain events that were appended to the event store and projected into view models. Finally, the comment result was communicated from those read models back to the users. So those were the so-called one-way commands. But the thing is, there is no such thing as a one-way command. One-way command is an event. A system should be able to refuse execution of a command. And of course, communicate back to the user the reason why it was refused. Was this, I don't know, an infrastructural issue, or maybe the command was invalid? And if it was invalid, then what are the validation issues? How can he fix those errors and submit a proper command? So our users were also, you know, they were not really happy about this CQRS thing because they expected to get results immediately. For example, if a sales agent executed a command which changed state of a customer, well, he expected to see the result of this operation displayed immediately on the screen. Once he got this OK from the server, naturally he expected to see the updated data on his screen. And that's understandable. So, at some point, again, we decided that this system needs a change. So, to fix this, we implemented proper commands. Now, they were executed synchronously, and the execution result was delivered immediately to the user as part of request-response model, a simple RESTful call. Now, moreover, in some cases, the execution result not only returned the execution result of the command, did it succeed or fail, if it failed, why, but also we returned updated data as well, which was supposed to be displayed on the UI. Now, here's the tricky part. That was like a shortcut, because according to everyone who is doing CQRS, that's something that you are not supposed to do. However, if you're returning data that originates from a strongly consistent data store, the event store, then you can just return it. There is no point in waiting for it to be projected into those read models. The limitation is you cannot return projected data. Why? Because, again, you're returning the result as fast as possible, but projections are asynchronous, and it will take time to propagate those changes across all projections. So physically, you are not able to do it. You can only return data from a strongly consistent store. And again, the result of this was a much better user experience for our sales agents. Now, let's talk more in depth about this projections thing. The CRM system published those domain events which were used for event sourcing as its public API. And it expected other systems to leverage that freedom of generating their own projections. So here we have 100 different event types. Do whatever you want. Good luck. And of course, this honeymoon period ended very quickly. At some point, we realized that 90% of those subscribers were projecting the same model. Despite the freedom to adapt, they stick with the same model which was used by almost all of them. And again, as in the case of marketing system, this introduced logical coupling. The logic that projected events into a workable state was duplicated in all those subscribing components. Not only it was duplicated, but because it held in knowledge of how each domain affects the state, it was coupled to the CRM's implementation details. And as a result, it caused another type of coupling, implementation coupling. All those subscribers had to closely follow changes in CRM's implementation. If a new type of events was introduced, they had to reflect this in their code as fast as possible. Why? Because if a new event can affect the value of some of their fields that they are projecting, ignoring this event eventually will lead to inconsistent data, something that usually business people are not really happy about. And finally, we have here a third type of coupling, and this one is a more subtle one. I call it semantic coupling. Some events in the CRM system were not defined clearly, and subscribers had to make assumptions on meanings of those events. For example, we have this event here, agent assigned to lead. Now, the question is, what does it mean when a subscriber receives 3 such events? Does it mean that 3 agents are assigned to the lead, or only the last one? the event, its schema doesn't, tell this difference, doesn't communicate this knowledge. So the subscribers had to make assumptions on the implementation details, and sometimes they made different assumptions. So to sum it up, if we were to evaluate this architecture, again, it screams at us high global complexity. Despite messaging and all those services, all systems components are again tightly coupled to each other because of implementation, logical, and semantic couplings. Now, to decouple this mess, what we did is we encapsulated the state projecting logic in the CRM system itself. So instead of exposing its domain events, it published changes to the projected state through event-carried state transfer. Effectively, the CRM's public API now compressed its implementation details, those domain events, into a more restricted and limited set of public events, which were just used to notify subscribers about changes in the state of those entities. Of course, it did raise the local complexity of the CRM system. Again, we moved some logic that wasn't there before. But again, that's nothing really serious because, first of all, it's really coherent with what was there in the first place. It all works and operates on the same data, on the same schema, and usually both the original code and the new one, they're changing in the same pace. So this change didn't have any considerable effect on the local complexity of the CRM system. However, this refactoring dramatically reduced global complexity of the whole system because, again, we removed all those sources for couplings between those components. Next story. One day, our managers decided to try working with a new business vertical, to evaluate a new way of making money. And for that, they needed a new system. So this system was defined in domain-driven design terms as core business domain. That's how our company was going to make money. So technically, we had to invest our most advanced tools in design of this project. So back in those days, this microservices trend started appearing. We heard about those microservices superhero companies doing great stuff with this pattern, so we decided to give it a try. So we decomposed these business domains into those tiny, tiny services. Why tiny? Because micro, right? It should be small. And we actually there was not only asynchronous communication between them, also some of them communicated synchronously, but that doesn't really matter. Over time, however, all those microservices became more and more chatty, and more connections started adding up between them, until at some point almost all of them needed data from all other services to complete some of its operations. And as you can see here, global complexity of this solution skyrocketed. Suddenly, all those systems components became entangled and very tightly coupled to each other. Now, it was really hard to change this decomposition, and we were really optimistic. We thought that it will be better soon. It wasn't. Of course, the solution was, first of all, to realize that we naively decomposed the system without being familiar enough with its business domain. So those boundaries were wrong from the beginning. And what we had to do is to merge them together, to lower the global complexity of the system, to raise the local complexity of this component, but only then, we could decompose it into a more limited set of components with more coherent business behavior in each of them. For the fifth story, actually I cannot trash talk too much because I wasn't involved directly in this implementation, so I will try now to restrain myself. Okay, never mind. About a year ago, our company was merged with another company, and that new company was building a trading platform. And here's what I stumbled upon when we were doing architectural reviews. The system would process commands from its users. Those commands resulted in a transaction against a relational database, and then events which were published to a message bus, Kafka in this case. And of course, the goal of this distribution here was to create a distributed system, a scalable system, and overall modern architecture. Now, the obvious problem here is we have transactional coupling here. This operation assumes that it can be executed in the same transaction, which it can't. Infrastructure-wise, without going into distributed transactions, you want to keep it sane. So implementation-wise, it wasn't possible to guarantee this transaction against two stores, a relational database and a message bus. And what happened if the server went down in the middle of processing one of the commands? If it already committed data to the database and then the server failed, before publishing the events, none of the subscribers had any clue about that operation. Those events, not only they were not delivered, they didn't even exist at all in any place. There was no trace of them. Now, also, the order of the events here is important as well, but again, it wasn't enforced in any way by the producer. Those events were just generated, not stored in the database, just generated in memory and published. And of course, we cannot use timestamp for ordering the events. The system runs on multiple servers, and each server can have a different local time. So that introduced an additional dimension of transactional coupling. This system assumed that all consumers will process the events in the same order as they were published by the producer. Now, let's see what those consumers are actually doing with those events. So the first one is committing the events into some kind of backup database. Nothing really interesting, pretty boring. The next one, however, projected a state out of those events and stored that state in a cache database. And the last subscriber, which was used to process events for the analysis systems for the BI, what it did is when it received the event, first it would enrich the original event from the state from this cache right here. Now, what happened is this last line here actually introduced temporal coupling in a distributed system, in an asynchronously communicated system. Those events can be processed by this analysis subscriber only after they were processed by this state generating subscriber. And of course, it's very challenging to implement, so no one really did it. As a result, the events that were submitted to BI were enriched with the wrong state. Not always it reflected the most up-to-date state from this cache. In other words, it corrupted data. And of course, the simplest solution here is the outbox pattern. To leverage the relational database, which is already used by the system. So when the system modifies some state in those relational tables, to add an additional table called outbox and write out all the events that are about to be published as a result of that operation into that event, into that table. And then after this transaction is committed, some relay can pick up those events from that table and publish them to the message bus. And this way it decouples all those, logical and transactional couplings between those components. And the last horror story is about a nice microservices-based system. It was really nice, seriously. It had low global complexity. Those microservices were really coherent. They were not really coupled with each other. And, local complexities of the services themselves were pretty low as well. A dream. However, one day we had to introduce a new microservice. And that new microservice had to process data from all of them. It had to subscribe to events from all those services, do some magic, and then communicate this magic back to them asynchronously. So what happened here is this new microservice introduced a hell lot of implementation coupling which spanned across all of this system. So what was a properly decomposed system became an entangled distributed monolith because one properly designed service. I call it architectural Trojan horse. The solution that we picked was to use domain-driven design anti-corruption layer pattern, to separate the integration complexity from the business complexity of the new service. So this layer right here, what it did is actually collected data from the rest of the system, transformed it into some workable state which was more convenient for this new microservice. And in that way, this new microservice, which was pretty complex, it has very complex business logic, it was decoupled from the rest of the system. The coupling was the coupling to the rest of the system was here by this anti-corruption layer, but because there was no complex business logic here, it was something tolerable. Anyway, it was much more convenient than this previous scenario. So that's domain-driven design's anti-corruption layer. So now I finished with those scary stories, and to summarize them, I want to share 3 rules of thumb that actually sums up all the problems that I've just shown you and the solutions that we used eventually to solve them. So first of all, when designing event-driven systems, be pessimistic about everything. Do not naively assume that everything will work. No, things will fail all the time, and usually on Saturdays. This optimistic consistency model, as I've shown you here, it can be called, data corruption. It will corrupt the data. And usually when you encounter such problem in the design, people will tell you, yeah, but how often will it happen? If we have 1% of those events being lost, who will notice? And that's the scary shit, because the system is going to corrupt the data and no one will notice. So don't rely on optimistic consistency. Make sure those events are always delivered to the subscribers. The word driven is there in event-driven architecture for a reason. Make sure those events are delivered to the subscribers no matter what. Now, some events can really be implementation details, especially those domain events as in event source systems. And it's usually tempting, to expose them as public API. but you do not want external systems to depend on your implementation details. You need to be able to change the implementation details as you are working on your requirements. Your clients, on the other hand, expect to get a more stable API, which is not going to change often. So therefore, use some events as private implementation details and other events as public API. And again, private can be very detailed domain events, like many of them, many different types of events, and you can change them as you like. But for the public API, compress those private events into a more restricted and a more stable of public events. And of course, use the correct type of events for your need. In this case, event carrier state transfer is the better option for integrating services. Now, if you are going to neglect this and choose wrong event visibility, it will introduce logical coupling between the system's components. It will lead to, over time, it will for sure lead to duplicated logic between your system's components. Now, instead of going async by default, when integrating services, evaluate their consistency requirements. So if you're integrating two microservices, what happened here? Sorry. Speaking too passionately about it. If you have two microservices and when integrating them, eventual consistency is acceptable, that's great. Use asynchronous communication through events. And of course, event carried state transfer is the natural choice for such communication for integrating them. If, on the other hand, you have two microservices and one of them always expects to read the last written information by the second one, it expects to read the last write, then you have a bit more challenging situation. In this case, you cannot just use those event carried state transfer events and deliver them asynchronously. In this case, the simple thing will be just to issue a synchronous call, a GET request. Give me this data, and you will always receive the most up-to-date information. Another option would be for the source to publish an event notification saying, hey, something interesting has happened, but if you're interested in the data, call me synchronously and I will give it to you. And finally, if you have two microservices and there are some operations which cannot be executed concurrently, like one operation in one service, another one in the second, you cannot execute them concurrently. Only one can be executed at the same time. Here, stop whatever you're doing and merge those services together, because that's the shortcut to enormous global complexity of the system. And to wrap this whole thing up, I will go very briefly about everything I've shown you. So software architecture's goal is to manage complexity. Software architecture divides systems complexities into two types: local complexity, complexity on the component level, and global complexity is level of interconnectedness between the system's components. There are three types of events: notification event, which says that, hey, something interesting has happened; event carried state transfer for publishing changes in data between services; and domain events, which notify that something interesting has happened in the business domain. Again, they're somewhere in between those two previous types. Design heuristics: first of all, be pessimistic. Assume that things are going to fail, and make sure that your system is delivering the events no matter what. Use private and public events to limit the public API of components, and evaluate consistency requirements to choose the correct way of integrating services. And I think I'm done here, and we have 5 more minutes for questions, if there are any. 1. Yeah. Yeah, so look, that's a great question. And before diving into an implementation of those events or systems, we always evaluated the expected lifetime of those business entities. And for example, in our CRM system, we would like our customer to be long-lived, to have transactions which will span years, but usually their lifespan is limited by, let's say, 100, 200 events. So we just maintain the state. It's just cheaper to keep it instead of doing those generating snapshots or archiving it. And in another system, in the commissions module, we have this detailed monetary transactions. And there actually, we to pay less for storage, we have to retire some of the data, archive it. If, for example, a sales agent is no longer working for us, no point in holding it there. We just move it to a file from the database in a flat file, and that's it. Does that answer your question?
So it does answer one facet of it, but the other is
You mean?
100 events get published out, they only consume 50.
Oh, that's a great question as well. So when you're publishing those events, usually you can publish it. Okay, so the question was, if, let's say you have an event source system, which is not only events, any system which publishes the events, how the subscribers can fetch the events that were lost because of some infrastructural issue. For example, servers went down. How does it know that, okay, something has missed? So the first and easiest option, is to introduce a queue. Each subscriber has a local queue which belongs to the subscriber. So when it goes down, it goes back up, it just reads the queue again. That's the easy part. However, that's asynchronous publishing of the events through this queue. However, we encountered some situations where, for example, subscribers had bugs in their business logic. So they couldn't rely on this queue. They would have to ask the publisher to republish all the events, and publisher will say, no, I'm not doing it. So in such a case, we always prefer the event source, the publishers, to expose 2 APIs for the event. First one is asynchronous through queue, and second is what's called catch-up subscription. We're just querying by some timestamp. So you always keep the last record, ID of the record, and you can always get the delta, what happened after it. And you can reverse it the other way. Does that answer your question? Any more questions? 1, 2, 3, sold. No more questions. If I still didn't bore you to death enough, you can follow me on Twitter. I blog about this stuff. Recently, I was honored to participate in this book project where I wrote the story of our company, but more from the domain-driven design perspective. And this book is really free, so there is no reason of forgetting it. That was my little shameless plug. Thanks so much.